Okay, so we're in section D, Introduction to Discrete Random Variables. So random variable takes on values that describe the outcome of a random process. It's a somewhat generic term. The probability distribution is all the possible values of their probabilities. So we sometimes draw histograms for that. Sometimes we write it in tables, but we can write out all the possible different distribution of that probability of some random event happening. So a discrete random variable takes a countable set of possible values with gaps between them on a number line. So it's something you can actually calculate. So this is probability of list of values. So you might have a bunch of different values. You might have the probabilities of those values. Might be for different rolls of the die. Might be for just about anything. So for the probability distribution to be valid, similar to what we talked about with valid in general probabilities, it has every probability has to have between 0 and 1, and the sum has to add up to 1. So very similar to what we've had before with that. X is the number of heads and in 3 tosses of a fair coin. So so X is the variable recording, the random variable is the number of heads if you toss 3 coins. So the most it could be is 3, the least it could be would be 0. So it could vary anywhere from this random variable, and it goes anywhere from 0 to 3. So you could actually just write out a little table here and go, okay, what are the possible numbers of heads from 0 to 3? And then you could calculate each one. And if you need to, you could actually, if this makes sense, you can write out the sample space. So oftentimes it helps to do that. So you might say, if you're flipping 3 coins, right, you might get heads, heads, heads. You might get heads, heads, tails, heads, tails, heads. There's one more head there, heads, tails, tails. And then if you do the T's, so this one starts with a T, so TTH, THT, and THH. So it looks like there's 8 possibilities. But as far as number of heads, this one has 3, this one has 2, 2, 1, 0, 1, 1, 2. You can see there's 3 2s, there's 3 1s, 1 3, and 1 0. So that's where these probabilities come from. You can write out the sample space and kind of go, okay, we can see that there's 1 out of 8 is 0, 1 out of 8 is 3, but 3 out of 8 are the 1s and 2s there. So that's where they got that from. They essentially wrote out the sample space and thought about it. Those sum up to 1, right? And all of them are between 0 and 1. So that's a valid probability random variable there, or discrete random variable. In 1952, Dr. Virginia Apgar suggested 5 criteria for measuring a baby's health at birth: skin color, heart rate, muscle tone, breathing response. I remember one of my boys was jaundiced. I think that's like a yellowish color. I feel like we had to put him in the sun, or kind of like, make sure he got a little sun there early on just to get his color back to where they wanted it. There's certain things they want when you're born that they consider healthy, and those are the 5 areas they sometimes look at and give you what's called an Apgar score. She developed a 0, 1, 2 scale to rate a newborn on each of the 5 criteria. And so that the max score you can get is a 10. I think it's tough to get a 10. But if you're up there, towards the top, that's pretty good. If you're down towards 0, that's potentially pretty bad. But if you're kind of like just a little bit below, that's fine. What scores are typical? I don't know. So I don't remember exactly. I remember they gave us a score when we had our baby. So define the X is the Apgar score of a randomly selected newborn baby. So our random variable we're scoring here is the Apgar score. We know the lowest is 0. The highest score you can get, the very best, is 10. That means you're super healthy, evidently. So these are the different probabilities of those happening. This is just from like experience. Oh, they didn't put the 0 there. Could we figure it out? Yes, because we know all those probabilities will add up to exactly 1. So if you add up all 9 of those that are given, subtract it from 1, you should get the missing score there, which I'm sure that's what they're going to do. I'm not going to show you that because it's pretty easy to do there. So they didn't show all of them there. I was trying to figure out what's happening here, but they should have added up all 9 of those scores and subtracted it from 1. I'm not sure why they just pretended to add up 3 of those. There should be a dot, dot, dot there, right between the 0.007 and the 0.053. They should have added up all 9 of those and subtracted from 1. I'm not sure what's going on there. Doctors decided that APGAR score of 7 or higher indicates a healthy baby. That makes sense, actually. I think that's about right. What's the probability that a randomly selected newborn is considered healthy? Okay, so essentially they're saying 7 or higher. So what do you do to get that probability? Well, you're just going to add those probabilities up. The probability of 7 plus 8 plus 9 plus 10. The probabilities of all those scores. So you just add the 0.099, 0.319, 0.437, and 0.053. And if you add those up, you get, wow, 90.8%. So a little over 90% of babies are 7 or above. So, and I think all my 3 boys were 7 or above. If you're seriously below 7, usually indicates just, some things are going really wrong, if that's the case. But it's okay to be just a little bit below, I think. Lots of times you can just kind of put the baby in the sun. Yeah, you fix that one. There's different things you can do to kind of help them. Lots of times, like pre, what's it called when you go early? I think when they premature babies, I feel like preemies tend to be maybe below 7, just because there's some issues sometimes with their breathing or different things that might be going on. So that's oftentimes when you have scores below 7. Probability of choosing healthy, that's from my experience. I don't know what I'm talking about. Probably choosing a healthy baby is, again, we did that. This is not the same as the probability that APGAR score is greater than 7, which is just the 8 plus 9 plus 10. So the first situation was 7 or greater. Remember, they said 7 is okay, 7 or greater. So those are slightly different. So you have to just decide what's the question asking. If it's saying greater than 7 or greater than or equal to 7, those are 2 different questions. So I guess only 80% or a little over 80% are greater than 7. When looking at the data, we can display this probability using a histogram. So you can actually do a histogram. So if this is the data, so the way you would do this is, let me just kind of get this ready. Okay, so let's see if we can do this. So on the bottom of the histogram would be the APGAR score. APGAR score. And you would go from 0. These want to be sequential. 1, 2, 3, 4. Wait, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't just do whatever the scores are there. I mean, well, in this case you do, but if they're not sequential, you still have to make a sequential x-axis. So that's always true. Just that's how we roll with x-axis. It has to be sequential. So then this would be percentages, right? So because the biggest percentage we have is not that big, which it looked like. So 7 is probably pretty common. So 8 and 9. So 43, so 0.5. So 1, 2. So maybe that's 0.5 or 50%, 0.3, 0.1, etc. So then you would draw these kind of like a histogram kind of thing here. So 0.001. Well, it's going to be hard to draw that, but it's 0. I guess I should have gone a little left of there, but it's like 0.001, just barely there. 0.006 again, barely there. 0.07, barely there. These are so small, it's almost impossible to draw. That's for 1 and 2. 3 would be again, so small. So that's not even 1%. So it's super small. I'm sorry, it's just really hard to draw. 0.012, again, so small for 4. 5 is 0.02, so that's 2%. We're getting a little bit higher, so I guess a little higher than that one. 0.038, so we're getting a little higher, so we're like getting up there. Okay, so then that's 6. 7 is almost 10%, so right up to about where that bar is there. Then 8 is 31%. Finally we're talking here. So somewhere in that neighborhood. 9 is 0.437, so again, a little bit higher there. And then 10 is 5%, so it's pretty far back down. I don't know, it's really poor drawing, but this is the probabilities over here. So probabilities as decimals or percentages. Let's see what their graph looks like. It should look better than mine. It looks pretty similar though, right? I mean, it's just really hard to draw those really small ones when you're drawing that. They left a little more room for 0 there, which is probably a smart move. It's a veteran move right there. I forgot that we had a bar at 0. That'd be 0. Ooh, I wonder if it maybe at 0 would even be alive or not. I'm not sure. Distribution is skewed to the left and unimodal, right? So we know that it's definitely skewed left. You can tell that it's unimodal. With single peak at an Apgar score of 9, that's the most common. It does help us kind of see the most common scores there pretty easily. So we can see lots of 7, 8, 9s. 10 is the next most popular score. So you can see most of the scores are up there. Pete's Jeep Tours offers a popular day trip in a tourist area. There must be at least 2 passengers for the trip to run, and the vehicle will hold up to six passengers. So Pete charges $150 per passenger. So C is the total amount of money Pete collects. So it's going to depend. You're not going to collect 0, so that's not possible. But 2 passengers would be 300, right? 6 passengers would be 900. So it's going to be between 3 and 900, I believe, for the amount of money he collects. Yeah, 3. 900, yeah, and they went by 150s because every passenger counts as 150, even though that could happen. I guess you could have a odd number of passengers. That's possible. Okay, so the probability distribution of C is given in the table. Okay, so that's just like from the data that he's collected from over the years. That's typically how he sells his things. So it seems very uncommon. Only about 5% of the time does he get all 6 passengers. That's beautiful for him when it happens. But much more common, maybe have 4 passengers there, and again, so forth. So those are the breakdowns. So make a histogram of that. So again, you would draw make sure the x-axis is sequential, like in the same. So you're going up by 150s there. So 150, 300, 450, etc. And then the probabilities on the left-hand side. The largest you need is 35%, so you could scale it accordingly. They went up to 40% on the left. But you just draw it. And this really gives you a much better picture. It's hard to look at that table and kind of see, I don't know, just see the popular choices or how the distribution looks. Now I can kind of see the distribution in a histogram, and that's pretty nice. Just to look at the histogram there, but it is pretty easy to make. It's not hard, so I feel like that's the first skill here. Describe its shape, so approximately symmetric, unimodal, with a peak at 600. Okay, we got that. Remember, values don't go on the horizontal axis, and probabilities go on the vertical axis. The values of the random variable go on the horizontal axis. So probabilities are always on the y-axis there. Label and scale each axis. Okay, that's the lesson. So that was pretty straightforward, not too bad a one. So write the events. Household owns 1 vehicle in terms of V, then find its probability. So we want to find that missing probability. So you're going to get your calculator out, add those up, subtract it from 1 or 100%. And so if you do that, the probability that V equals 1 is 1 minus all those things added together, or 1 minus 0.66, which is 0.34. So now it's a valid probability model because all the values are between 0 and 1, and they add up to 1. What's the probability the randomly selected house owns at least one vehicle? At least one includes 1. So you're going to add up the 0.34 plus 0.37 plus 0.14 plus 0.06. Or they did the complement, 1 minus 0.09, which is kind of nice. If you don't know what 1 is, that'd be a nice way to do it. It's the opposite of 0 is at least 1. That's actually hopefully one thing you learned in the last section or last chapter. If it's at least 1, it's the complement is 1 minus probability of 0. So that's actually really helpful in this passage, this chapter as well. The game of Chuck-a-Luck has been around since the Civil War. In this game, you place a bet on an integer from 1 to 6. 3 fair-sided dice are rolled, and if one or more of the dice shows your number, you win. The table below shows the probability X for the payout in dollars for a $1 bet of Chuck-a-Luck. The payout includes $1 bet by a player. Okay, so make a histogram of the probability distribution, describe its shape. So I just need to understand this game. So place a bet on an integer from 1 to 6. 3 fair 6-sided dice are rolled. So 3 dice are rolled. If one or more of the following of the dice shows your number, if one or more, so if like 2 dice show or 3 dice, you win. Okay, so seems like you're going to win, I don't know, half the time-ish, maybe. The table displays the probability distribution for X, payout for $1 bet of Chuck-a-Luck. So probability of X is 0, so that's going to happen. Sometimes you get no numbers the same. I'm still confused on what X is. X is the payout. Oh, X is the payout. Oh, so my guess is there's a 57.9% chance that your number doesn't show up. There's a 34.7% chance that one of your 3 is the number you picked. There's a 6.9% chance that 2 are the same as the number you picked. And every once in a while, about 0.5% of the time, you get all 3 numbers to roll. Okay, so X is not the die roll, that's the payout. You get $2, $3, or $11. Wow, you get $11 if you get all 3 the same, like a Yahtzee or something. Okay, so make a histogram of the probability distribution, describe its shape. So again, you're just going to make a histogram of that. Fortunately, the game was calculated for us. And so the x-axis is the x variable there. You have to make it sequential. So when you make your scale here, when you're making this, I just want to make sure you understand this thing. So when you do that, and that's your x, which is your payout, so to speak, it's how much money you get. Start at 0 probably, or even before 0, but 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You have to have at least 11 tick marks there because you're going to scale it out appropriately. Again, on this side, you're going to do, the biggest one we have is 57.9, so 1, 2, 3, 4, 5, 6. So maybe that's 0.6, and these are probabilities. And then you're going to scale it out. You're going to make your history bars, but your bars are not going to be all connected here because you get a bar at 0, 5, something like that, and a bar at 2, so 1, 2, so like here, 34.7, and a bar 6.9 at 3, so I don't know, that's somewhere up down here. And then 11, you have 0.005, so it's very small. I don't know. It's hard to draw it that small. See if that looks anything like it. Yeah. So again, make sure that you scale. I think that the biggest mistake I see on this is they forget to label. Students will forget to label what that is. I put the unit, that's a great idea. And then scale out the x-axis accordingly. Don't just put the numbers 0, 2, 3, 11. I think that's the biggest mistake I see on this kind of problem. And then describe it, right? The distribution of payout is strongly skewed to the right with a single peak at 0. So that would be the distribution described. Okay, that's your lesson for today.